All right, so yesterday, all we did in class for 2.4 was we started developing the intuition. And I gave us a quadratic, x squared plus 1. I know what this quadratic looks like. It's just a quadratic that's shifted up 1 unit. It's the parent function. And then we tried to find the roots, and we saw that, they don't exist. Kind of. Now, when we say they don't exist, really clearly, we're going to say they don't exist in the real numbers. Okay, again, it's just language. The real numbers, we could have called them the purple numbers, and it meant the same thing. We would just all refer to them as purple. They're not, maybe, I don't know. But purely a language thing. What we are really knocking on the door of is pulling off the blindfold that you've seen your whole life. You've used the complex numbers every day that you've ever used a number. You've just never been aware of it. So we have a little of our intuition. We're going to jump in, and I know it's redundant, but we're going to go ahead and define for ourselves the complex numbers. If you don't want to write complex like a million times, what is the blackboard letter that we use to represent these?
C.
A C. Now, the blackboard letter, all that means is it's the double bar letter. So whether it's the R for the real numbers, the Z for the integers, the Q for the rationals, or the C for the complex, we have these complex numbers. Now, for these, the definition is pretty straightforward, but it takes a lot of practice to get used to working with them. We are going to define our complex numbers, or the complex numbers rather, as numbers, the numbers, of the form. And I'm going to change color for this one just so it stands out, because this is like the most important part. It's all important, obviously. I wouldn't talk about it if it weren't. But the complex numbers of the form A plus BI. Okay. This is what a complex number looks like. A plus BI. Where A and B are real numbers. And I would use the blackboard R if I were you. That's this thing. And I, that lowercase kind of italic-y looking I, this thing is the imaginary unit. Now, yesterday's whole discussion about the reality of words and numbers and stuff was only there to motivate the fact that this is just a word. We could have called these the Kyle numbers, and it would have been completely fine. Quaternions is where they came from, not our real focus, but we call them imaginary. It's a terrible choice. They're just as existing as any other number, though. Okay, I is the imaginary unit. Okay, now with this, when we go through here, I made a claim a minute ago that every single number that you've ever dealt with is a complex number, which means it is written as A plus BI. Give me a number that you don't think is written that way. 1. 2, sure. So you're giving me real numbers, right? 1, 2, 6, negative 3, pi. All those are real numbers. I think they're actually complex.
Why?
Because if I wanted to say 1 is a complex number, and it is, I assure you, but that's like me just saying it's 1 plus how many of these i's?
0.
1 plus 0I is a complex number. It happens to not have the imaginary part to it, and you've been dealing with these your entire life. You've just never had to think about this plus BI part of it. It's been a 0 your entire existence until right now. Cool. All right. Now, we need to dig into this imaginary unit. And we saw yesterday where it came from. If it hasn't clicked yet, that's okay. Let's define it real quick. The imaginary unit and again, I really want to stress, if you like to change the way that we write stuff, normally it's okay. Use a lowercase italic looking I for this. Okay. Now, the imaginary unit, it shows up all over the place. And I want to remind you, if it didn't click or if you didn't catch it yesterday, if you want to study electricity at all, this is the type of numbers that you use, the complex numbers. Now, again, imaginary is just a word. They exist all the same as every other number and every other word, every other human construct. They exist the same way. As we look at these, it is really easy to define. The number I is defined to be exactly the square root of negative 1. It's not that it doesn't exist, it's that it's just called I. Now, when your calculator tells you you have a domain error, it's because your calculator works in the real numbers only. It doesn't deal with any of these i's, so it doesn't say when you type in square root of a -1, your calculator doesn't tell you this doesn't exist, it's undefined, I can't do it. It just says that there's a domain error because your calculator doesn't have the ability to work into the complex numbers. Other calculators do, yours don't. Okay, so when we look at this, it turns out there's some pretty handy stuff. We're going to do some scratch work in this grassy area over here. This is all scratch. You should have some scratch work as well. If you'd like a piece of scratch paper, you can go grab one. But we're going to play around with something real quick. This is going to seem like a completely left field question. You guys have never heard the terms modular arithmetic. I'm almost certain of it. You've heard arithmetic, but if I said it was modular, anybody know what I'm talking about? Ooh, maybe.
Right? Modular is where you can like move it and change it, right?
So, kind of. So, a lot of stuff comes in modules, right? They're just parts. Now, when we're looking at this, how many of you guys use 24-hour time in your everyday life? Like, instead of saying it's 4 p.m., how many of you go it's 16? Okay, I think it's way better, realistically, because it's no ambiguity with it, or it's not nebulous, if you will. As we go through this, though, see, we drop them now. As we go through this, I think that everybody, do you know how to do military time or 24-hour time?
Yes.
Okay, so let's pretend we're at 10 a.m. and I'm gonna go 6 hours in the future. Normally in military time, it's really easy to do. 10 a.m. plus 6 more hours gives me to what? 16 hours, or 1600 is the way it's commonly called. Now, using regular time, if I go 6 hours past 10, what time is it? 4. Now, how did you do that? But 16
I got
was.
to 10 and then I added the rest.
You got to 10 and then you added the rest. I think you
way
got to
more.
12 and then added the rest.
Yeah.
Okay,
I got to
so
12.
does everybody agree with 1600 is the same thing? It's 4 p.m. That's 6 hours after. Now, let's try one more. What's 7 hours after 3 p.m.? So 10 p.m. in our time, right? Or I could say what's 7 hours after 22? 22 is 10 p.m. What's 7 hours from that? Yep. Did I say 5 the first time? I think I must have. All right, here we go. We're going to write it down so I don't forget. If we're at 10 p.m., or if you'd rather, 2200 hours, and I add 5 hours, there, we'll stick with 5. What time do I get here? 3 a.m., okay? So, what time do I get here? You're going to get 3 a.m., but do we agree it's 2700 is what you, like if you wanted to do it? Well, we know that doesn't work because we restart, right? So we would call that 0300. Okay. Now, looking at this, without being aware of it, you're actually doing what is known as modular arithmetic. And it happens all over the place in computers. We're going to see it happens with this number I as well. When you go from whatever time, military time, and you keep it in our regular stuff, every time you get to 12, you restart, right? When we think about modular arithmetic, it's almost the same as clock arithmetic. We get to 12 and then we restart counting, right?
Yeah.
Okay, that is what we would say mod 12. So if I want to know what 25 is, mod 12, what I'm really doing, and what you would really be doing, and you did it earlier without thinking it, is I would take 25 divided by 12, or 24 in this situation, and I get a remainder of 1. So 2,500 hours is just 1 a.m. if we wanted to do it. Let's try it better, easier one. What time is this? We'll say 1,700 hours. What time of the day is 1,700? 5 a.m. or p.m.?
Yeah.
Okay, so how did you know that? So I don't think you really memorized it.
I don't know, I just.
How many past 12 is this?
5.
5. So that's one way to do it. Another way of doing the same thing but being a little bit more clean with our operation. What's 17 divided by 12? It's 1, right?
Yeah.
What's the remainder?
5.
Are you sure it's 7?
What? He says 17 divided by 12 is 1?
Yep, because it only goes in once, right? And then what's the remainder? 5, and it's 5 p.m. Like you're dividing by 12 and using the remainder. Now, that might feel like it came out of nowhere, but I'm going to give you guys a couple minutes. We're going to do some scratch work here, and we're going to work out two things. One, something really handy that makes these easy to evaluate. But second, I'm going to show you the name of, if I were to ever publish an autobiography, I'm going to tell you what it would be named. But let's start here. Don't write this down yet. I just want to think. In pink is just to think right now. If I have a number x, and that's to the first power, but we never write it. If I wanted to get x squared, what would I do? What could I multiply it by to get x squared? If we multiply this by x, would I get x squared? What if I wanted to get an x cubed? What would I multiply it by? I could just take this, whatever it was, and multiply by x again, right? So for example, if you're 855ers, you need to watch a video. You're going to miss some important stuff. I don't remember who all showed me the notes. But show me your note and peace out. The homework's on the Google Classroom already, okay? Cool. All right. We'll try to keep it short here for a bit. Sorry? One more time. It is recording, yes. Okay. If I wanted to get to x to the fourth, could I just multiply by x again? And I hope you use this when you're doing big numbers. Do you guys know what 2 to the 3 is right off the bat? 8. If I ask you to now evaluate 2 to the 4, do you just do 8 times 2 one more time, or do you restart at the beginning and do 2 times 2 times 2 times 2? Okay, can we agree that the first one seems like a much easier way to do it? If I know 2 cubed is 8, then 2 to the 4th must be 16. 2 to the 5th, multiplying by 2 one more time, is 32. 2 to the 6th, again, I'm just going to keep doing it, 64. Are you guys following that logic? Okay, let's use that idea. Here's what I want you to do for me. I want you to start with the following, and we'll go back into our scratch work. We're going to have I. Now, I know that I is equal to the square root of negative 1. Okay, it's just how it's defined. And I'm going to write it this time. We normally don't. That's I to the 1. Okay, I want you guys, using this same technique that we just did here, I want you to help me. I'm going to get us I squared, and then you guys are going to find I cubed and I to the 4th as well afterward. So help me out first. I want to get I squared as a whole class, and I want you guys to do the next two. If I wanted to do I squared, do we all agree that that is just I times I? Yeah. Okay, so whether or not you would actually take this small of a step is entirely up to you. It could just be I times I. Or do you agree that I could just take whatever this was and square it? Like there's various ways to do this. If I did this, there's I, and I squared it. What happens when you square a square root? They undo each other, right? That is the one place where cancel is kind of okay. Like, I prefer undo, but cancel works. They do just indeed cancel each other out, which means we just determined that I squared must be equal to what? Negative 1. This is I squared. If I wanted to get to I cubed, what would I have to multiply this by? 1I. Could I multiply it here by I since they're the same thing? I'm going to give you guys a moment. If you're struggling and you're not sure what I'm asking, please do. I want you to find the simplified version of I cubed and I to the 4th. I will come around in just a minute. I also want you, for fun, to do I to the 5th. So we'll see. Seemingly some people are remembering. Did you learn this in geometry? Yep, so let's check it. I'll come around and help as needed. All right, just backtracking real quick. With this one, it's just a definition. We just have to be cool with it. Accept it. This one, questions on how I got to I squared is negative 1. I just squared a square root, and now it's gone. Okay, now if I just multiply by I again, we're just going to get negative I. Everybody's still cool with that? Because I'm trying to work out these different powers. I'm just showing on the left I multiplied by I, on the right I multiplied by I. Again, one more time. If I multiply by I on this side, I get I cubed times I is I to the 4th. Everybody's still cool? All right, let's do this side. This is negative I is what we had. And what did I say we're going to multiply by again? I. So what does this turn into? Negative I times I. Negative I squared. Everybody's still cool with that? Look up at what we did just like 2 lines above. What did we just say I squared was? Negative 1. So do you agree that this is negative? There's my negative. And I squared we said was negative 1. So it's 1, isn't it? No or I. It's just 1 because it's negative I squared, but I squared is negative 1. So we have negative 1. If I keep going, And now I have this 1 right here, and I'll slide over. If I wanted I to the 5th, I would just multiply by I again, right? Notice what I get. I would get just an I. Because 1 times I again is just I. And if I went I to the 6th, I would get an I squared. Do you guys agree? I can't tell if I'm losing you. But I squared is negative 1. Okay, so if I did I to the 7th, I would be back at negative 1 times I is I. Because if you square the square root of negative 1, what happens with that symbol? And it just, we see repeat happen. Now, go ahead.
So it's pretty much 1, -1, -1, 1.
It is not pretty much, it is exactly that. Now, the way, if this doesn't click, come talk to me, because we're going to use it. It's my hope that everybody can see where these things come from, rather than me just telling you that this is what it is. They're odd, and I get that. Michael, question.
I don't get how you got I to negative that
This 1 or 2 or 3 or 4?
5.
5. Are you okay with how we got 1? So if I multiplied by I, because I wanted to get to I to the 5th, and I'll make my work a little bit neater here. Do you agree that if I take I to the 4th and I go by I, so we'll times I to the 4th times I, if I do the same thing on the other side, it was 1 originally, right? We already said that. And if I multiply this side by I better multiply this side by I. Okay, so now what's I to the 5th? I. That's how we get it. And if I do it again, I'm going to get an I squared out of the deal. Yes, sir.
So if I don't put like the i's process, I just do -1.
So we're going to clean it up so that you don't have to do this every single time. You're definitely not going to do this every time. Now, this is a lame joke, and I don't know if it really classifies as a joke. We're going to talk about what my autobiography would be. What's an autobiography? It's a book that I write about me. So a biography is a book about somebody, and auto means they write it themselves. Angel, last comment before we go into this.
I like the 7 to be equal to
Negative I.
negative. The other one is positive.
Yep, and we'll talk because there's an easy way to do this. Okay, now, what I recommend we use is the following, because if you don't like this, that makes sense. It's a new number. You've never seen it. Gross. Whatever. I get it. Okay, we're going to talk about the name of my autobiography. It'd be The Powers of I, which I think is a really cool name for a book for a math teacher, personally. I think that's awesome. You guys don't appreciate it yet. You will. Like 15 years when you realize how cool of a title this is, just let me know. Shoot me an email. Cool. All right. We're going to draw a circle. You guys can do math with a clock. We have a simpler clock here. I know it doesn't seem like it. Clocks, you restart when you get to where? Where does it look like we restarted with these? So once I get through 4, I'm just back to whatever I had originally, right? So check it out. The powers of I. Here's what we're going to do. Some of them feel silly, but we're going to start with I to the 1 equals I. And that's true. That's what it is. It's the square root of negative 1 or I. If we squared it and we only use the simpler term, if we look at all the scratch work that we just did, what do we claim I squared was? Negative 1. If we go one more step, we would get I cubed, which what did we claim I cubed was? Are you sure?
Negative I.
Negative I. And if we go one more step, we would have I to the 4th, which a moment ago we worked out. What is I to the 4th power? So negative I squared, which is negative 1, because I squared is negative 1. And what did we decide it was? 1. It's just a 1. Now, where this ties back in, and the reason we're talking about the clock stuff, is what we're seeing right now, instead of clock or modular arithmetic using 12 numbers, we repeat. Instead of going 12, we only have to go 4. This makes it incredibly easy to evaluate really big powers right off the bat. So, couple little comments, and we'll knock out some examples here. The first comment that I want us to make sure that we're super aware of is we will never leave I to a power bigger than 1. Never have I to some power bigger than 1. And that's a weird way to do this, but never let the exponent on an I be bigger than 1 in a problem. And the reason that we don't do that is because for every single possibility where it's I squared cubed to the fourth, doesn't matter. Every single possibility, it breaks down into one of these four. I would much rather deal with negative I than an I cubed. It is a simpler expression, smaller exponents, it makes stuff easier. Okay, other parts of this. It turns out that this, all of this right here, is really just mod 4 instead of mod 12 like a clock is. We can use these to evaluate in the exact same way that we did the clock times. Like you just divided by 12 and then use the remainder. The same thing happens here. So we're going to see a couple examples. I don't know that they'll show up this crazy when you get to it. Asking for the bathroom. Wait like 30 seconds. Okay, I want us to simply evaluate, and maybe simplify is a better word for this. Simplify. And we're going to see a couple of them. We're going to do our first one together. What's your favorite? Okay, let's see what I to the 6, 7 is. Cool. I'm just going to beat it in the ground. It's not going to be cool anymore. Just fully lean it. I don't know if it's cool now. People last way. Okay. Anybody want to go through that process here 50 or 62 more times? Me neither. So there's an easy way to do this. How many steps did we have in our cycle before it repeated? It was 4. How many steps on the clock cycle? And if we wanted to convert some time to 12-hour time, we just divide by 12 and use the remainder because it was mod 12 on the clock. This is mod, what number again? 4. So here's all we have to do. To find this, super duper easy. We are going to simply take 67, this power, divided by what number? 4, and use remainder. Every time, the powers of I are super duper easy to find because there's only 4 possibilities of it. So let's do a little bit of scratch work. What's the power of this? 67. Cool. And we're dividing it by 4. And here's something that you could use a calculator with, but calculators don't give reminders. Whoa, remainders. Weird. I don't know how to do long division anymore.
You try to do 4 fits into 67.
So that's the whole problem. Is there a simpler way to do it? Does 4 go into 6?
No.
Are you sure 4 doesn't go into 6?
I was one.
It goes in once, and then we put a 4 here, right? Because we just do 4 times 1,
Subtract.
and it's a 4. Now we subtract. What do we subtract? 6 minus 4 is 2, and then what happens with this? We drop it. Now the question just simply changes. Does 4 go into 27? How many times completely? 6 gets me to 24, and I subtract it. And what's my remainder? 3. Now, if we wanted to do decimals, we could, but we don't. We want to use the remainder. Apparently, what we've just found, and the language here, just in case you want it, we won't use this regularly, but what we've just determined is the remainder is 3. Or, more specifically, we could say 67 equals 3 mod 4. Now, you do not have to do this, and we will never bring this up again, but it's nice to see this scary language that if you ever take a computer science class and you learn to code, you will see this. Like 100% you will. Okay, so now that we know that 67 is the same thing as 3 when I'm working in mod 4, this is super easy. Instead of I to the 67, we just said that's the same as using what? So use 3 instead of 67. We're just using the remainder, the modulus of 67. So what we have then is I to the 67. That's gross. It's really the same thing as I cubed. And the good news is that we only have to run through one circle. Thank you, sir. Good to see you, by the way. What is I cubed based on what you have written on your wonderful circle of I? Negative I? Check it out. I to the 67 is just negative I, and we're done. If you can divide by 4, you can do every problem like this. Let's try one more general problem. Liam, you can go now if you'd like.
Does it say 0.3?
Does what say 0.3? Okay, one more. I want you guys to talk with one another. Talk with me. I'll come walk around. Let's get a bigger number. I want you guys to simplify for me I to the 234. I'm going to give you a moment. you're going to divide by some number, whatever mod we're working, and you're going to use a remainder. Vi. Whether you use calculator or long division by hand, I don't really care. I just need to know it's a 2. That means that this is the exact same thing as evaluating I to what power? 2. What is I squared? And look at that. I to the 234 apparently is just -1. We're just dividing by 4 using clock time on a clock with 4 instead of 12. Okay. Now, as we get going through here, what's up? You only use the remainder every time. Power divided by 4 and use the remainder.
So 50 doesn't go nowhere? It's just there?
Yep. So like if you want to, you could think of this number as being, how do I want to word this? It could be I to the 58 times I to the 58, and it was 4 times, right? I to the 58, I to the 58, gross, times I squared. That's the same as this number, but check this out. Each of these winds up being I to the 0 every time, which is, gosh, I to the 0 is, oh, it's anything to the 0. 1 times 1 times 1 times 1 times I squared. It's I squared. Like, it works nicely every single time. Okay, if you're getting hung up on that part, don't. The big deal that I need is we need to have these 4. Pro tip, if you want some sort of indication, there is a 100% chance that you should have this on your note card later in the chapter. I would make sure you have it. Now, the powers of I, make sure you have them. Okay, now this stuff, all we're really doing is dividing by 4, and it's nothing too crazy. I want to get more into the complex numbers instead. Yes.
I'm rewriting it so it's like
These will also be online as well, but I'll keep this up for a second. Okay, I'm going to add a tilde. We have just been working with the number I right now. Now, complex numbers don't just have an I typically. It's, what's the form of a complex number that we started class with? Something plus something. A plus BI. Okay, now, the cool thing is that just like we can do 2 plus 3, we can add 2 complex numbers as well. Now, you've actually been doing it. It's just every time it was plus 0i on all of them. So you never had to think about it. It turns out, though, that your intuition and your gut feeling for how this would work, or if you got to write the rules, I'm confident we would do the same thing. We're going to talk about some basic operations. And we could call these arithmetic if you'd rather, but I like operations in here. And I just said these are some basic operations in what? The complex numbers. Now, we're going to look at them. There are 4 really basic operations. 3 of them are pretty nice in the complex numbers, and it's going to work exactly like you want it to. What's the most basic of the operations? Addition and? So I'm just going to hit both of them on the same thing since addition and subtraction are the same operation. One's just adding a negative. Let's look at addition and subtraction. Now, I'm going to write the first part of this statement. We're going to try to define the rule here, but I want to see what you guys come up with. We'll do plus for our example, and then we'll add the piece to make it both. Okay, I want you guys to add the following for me and to physically write down on your page what you want it to be. If you got to write the rules, talk with your neighbors if need be. If I wanted to take 2 numbers, a plus bi, which I know it looks weird. This is a single complex number. And I wanted to add to this a different complex number. I have to change letters so I can see what's happening. Let's say this one was c plus di. All I want right now is when you guys look at this, I haven't told you how it works yet. I want to know, how would you want it to work? Chatting with your neighbors, really lightly, in pencil preferably, or in your margin wherever you do it. Write me what you think these add up to. How would you want it to work if you got to write the rules? I'll give you a minute. If we can do the 2 plus 3x plus the 1 plus x problem right here, this is exactly the same. When we combine these, we're just going to put same parts together, right? What are the 2 parts that aren't having I in here? So we could probably just do a plus c for that part of it, plus, what's the other one? So bi plus di, or could I do b plus d times I? And I know it feels weird to write it this way, but is that really what we do? Like if I wanted you to add these, you guys probably jump right to saying it's 3 plus 4x. I would guess.
Wait, why isn't it I squared?
Because are we multiplying or adding?
But are they technically multiplying?
They are not technically multiplying. Are you looking at this part is why you're wanting to do that?
Like they're right next to the BI.
So b times I is certainly happening, and d times I is certainly happening. But, Angel, it's just like these ones. Are you okay with these ones not squaring? If I do...
Oh, wait, no, wait.
Yep, same thing. Okay, when we look at these, this is all that happens. Now, we're going to do an example of it. Do you want an example of just this, or do you want to see one more operation, and then we'll do examples of both? Just this. Okay, I am going to sneak one thing on here. Instead of just saying plus, so we don't have to write the exact same statement twice, I'm going to call this plus or minus. So we're also covering the subtraction here is all, which means this plus sign should also be plus or minus. All right, I was 100% planning to give you homework tonight. I am 0% planning to give you homework tonight at this point in time. Our last problem of the day. I want you guys to simply find or evaluate, but find is shorter. I guess kind of homework. You get one problem that I want you to finish. Bring back done on Monday. It'll take you 10 seconds. I want us to do 2 minus 5i. So there's a complex number. Minus 3 plus 4i. This is your single problem for homework. You guys can start packing up and piecing out. We can't piece out for another 20 seconds. But bring me this problem done on Monday. Cool. Monday. Baller.